warm up, what I'm going to do is I'm going to, first of all, what I want to do is give the canonical example of an inductively defined type in a dependent setting. But in order to warm up to that, I want to start out with reconsidering the sum of two types. So what I want to do is I want to look at the, well, we've used different terms. Let's call it the binary sum. Yeah? Pardon me, what? What? Well, yeah, if I don't get started, people won't come in. So what I want to do is the binary sum, which corresponded logically to disjunction. And what I want to point out is that there's a generalization of the rule when you're dealing with families of types. So I'll assume you already have in your head the rule for the disjunction, where and then a case analysis with a fixed target type for the case analysis. What I want to point out here is that in the case of a dependent type, it's a little trickier. So let's look at the introduction rule. So we would have the introduction rule for the binary sum would be, let's say it's a plus b. This is really a warm-up exercise, what I'm doing here. And I'm going to do it's all an instance of an inductive type, but I'm going to like do it incrementally. Okay. So here's the idea. Let's call that n just to be, maybe it might be helpful. A plus b if n is b. Okay, so those are the two intro rules. So you're familiar with that. And if you read that as or, it's just the choices we have for the or. And the question is the elimination rule. And in the dependent case, the elimination rule is more interesting than it is in the non-dependent case. So the idea is if I have, you could think of it as a proof of a disjunction, or anyway, an element of this binary sum, which means it's either an A or it's a B, and it's marked according to which one it is. The reason for the marking is to ensure that I can do a case analysis. Otherwise, it makes no sense to make a choice. So what we're going to do is we're going to have two cases. So this will be just the syntax will kind of look like what you had. I don't remember or know exactly what Frank wrote, but I'll do something that I hope will look good. So what we're going to do is a case analysis, okay, which I will fill in, and it's going to have a type here. And the issue is, what is the type of the case analysis? So previously, what we did in the dependent case, I'm going to erase this. This is just like to warm you up. You would end up saying, well, I have a type, and we're going to have a compute a value of an arbitrary type C. That's what we did before, and then we would fill in something here. And what would we fill in? We would say, well, if X is in A, and if Y is in B, and then we'd have two cases. So we'd have maybe N in P, and this would be C, and this would be C, and then this would be X dot N and Y dot P, maybe. Okay, that would be a reasonable, that's at least my notation for what you probably already covered. So you know what that is. Okay, so that's what you did before. So that's the simple case. But when you're dealing with families of types, there's more information to be gained. And another way of saying it is, if we think of it, and here's how to motivate it. What we want to do is we want to think of this as an induction principle, okay? Because a case analysis is a form of proof by induction in which there are no inductive hypotheses, really. There are just cases. It's just degenerate. It's an inductively defined type in which there happens to be no recursion, okay? But the point about the inductively defined type is that you enumerate a fixed number of cases to consider, and perhaps they are also recursive. All right, so what I'm doing with this example is sort of let's suppress the recursive part. This is an example of an inductive type. Well, if we think of it as an inductive type, then what we're doing when we do a case analysis like this is we're doing a proof by induction on M. All right, and if you think about how proofs by induction go, well, what are we proving? We're proving C. But really, what we would like to do is we would like to prove the induction principle, to be fully general, wants to really be a statement about M, not just some fixed proposition C that is completely oblivious to M, but you want to say something about M itself, because that's the point of doing a proof by induction. So what's going to happen here is we're going to have M, let me use the variable Z, is we're going to say this will be a proof of C holding for M, C of M, a predicate C of M, where this becomes a predicate rather than a fixed type. So with Z being, let's write it Z being of type A plus B, C will be a type. Okay? So this is what we're doing. And then here, what we do is we want to flow the information into each branch of what we're doing. So in this case, what we're doing is we're trying to prove something. There are two cases to consider, in left and in right, uniformly in whatever they're in left of or in right of. Okay? So these are the two cases. There are no induction hypotheses, but there are two induction steps, if you will. We prove these two cases, and we prove them for the specific case. So it's in left of X for Z, in C, and in right of Y, I think I called it, Y for Z in C. And so that's the critical idea, okay? And the definitional equivalence is the same as what you expect. When you do a case analysis, you do a substitution. I won't write that out. But the important point is you get a more refined typing because you're trying to express the principle of proof by induction, okay? So is that clear? So it's props as types, right? So the thing that you need to be like really fluid about, and some people have rightfully criticized me for being a little too facile with this, but eventually you should be able to have a very fluid attitude about propositions and types. You should be able to see these things both ways according to what seems suitable in any moment. Okay, so this is a good example of that. So if you think of this as a proposition just because psychologically it helps, then it looks more like an induction principle. Now, you'll notice here that, I want to mention two remarks here. So this idea has been around for decades. It's been around, I don't know, at least since the 70s and maybe before that, okay? But it was sort of rediscovered a while ago in the guise of what are called GADTs. And there's some big falderall about this, and I find it rather tries my patience. Because the main idea is the idea of learning. The main idea is that when you do the case analysis, you know in the target type which case you're in. You flow the information that you're dealing with the in-left case into the type. That's the critical idea. Okay? That's what's important. The dependent elim has been around forever, and it's really an instance of dependent elims. Okay? So that's a worthwhile thing to mention. The other interesting thing to mention, if you would like to specialize for yourself, it's kind of useful. Let's look at the special case of 1 plus 1, which we could write as 2 for some reason. So think of it as A and B are both the unit type. So it's 1 plus 1 or 2, which is the Booleans. So this is a Boolean. So what we have is a choice of two types, one for when it's true and one for when it's false. And then what happens is when it's 1 plus 1, the x is of type 1, so we already know it's the null tuple, and the y is of type 1, so we already know it's the null tuple, so we don't really need to even have the x here. And this corresponds to plugging in true, okay, which is in left of null tuple, and this corresponds to plugging in false. And in that case, it's an if statement. If m, then n else p has type, and then the crucial thing is you plug in the Boolean itself for z in C. So this guy gets to know, okay, what m is. So in particular, as we develop ideas further, I don't have all the material I need on the board yet, but as we develop ideas further, this family could itself be a conditional under certain circumstances. So in other words, the type of an if might well be an if. Okay? And what it will do is it will branch on whether m is true or false and give you a type for n and a type for p, thereby completely eradicating like one of the biggest bugaboos, pointless bugaboos about type systems that supposedly it's some disastrous thing that you can't, that the two branches of the if might have a different type. Look, if you want to do that, then you have to have a more sophisticated type system. That's it. Yes? It's really hard for me to hear you, sir.
Why did we substitute in right by false?
Oh, because if I think of 1 plus 1 as being 2, then I'll say by definition true is in left of the null tuple and false is in right of the null tuple, just by convention. That's what I'll do. So I wrote true and false. Okay? Because x being of type 1, we already know it's the null tuple. There's only one element of type 1, so the variable really plays no role. so it becomes a constant that you're plugging in true and false. Okay? So the point is you get to do the conditional branch. All right, so that's very useful. We're going to put this thing, so to say, on steroids in a few minutes. So it's worthwhile to understand the core idea before I start getting really carried away. Okay, so is that okay? Are you guys okay with that? Okay, good. All right, all makes sense? All right. So next time you look at things like G80Ts or something, you should realize that they're desperately trying to do a broken version of dependent type theory. Okay? That's all that's happening. Okay, so good. So that's the binary sums. The next thing I would like to do is natural numbers. Okay? So I've held off on doing these for a long time because I wanted to get to this point. So if I were just trying to introduce natural numbers as some kind of data, then what I would do is this, and you don't mind if I'll start being rather terse about everything. So I'll start writing in, this will be nat introduction, for 0, and we can have a nat introduction for, there are different ways of defining this, but one would be if I have a number, then I can take its successor or something. That would be the typical way to introduce the inductive type of natural numbers. So the thing I want to point out is it's a sum, but it's a, so to speak, a recursive sum. In other words, the argument to this, there's two choices, 0 successor. The argument here is again one of these elements of these type. This is the inductive type, of course, and so that's why it's useful to isolate it. So this will be nat induction for successor, let's say. Okay, that part is not hard. Now, if I were doing only, so let's do only the sort of computational view, and I weren't worried about logic and getting it all to work in, so I'll work in I'll call this non-dependent. So this is the sort of thing you see in Gödel's T, if any of you know about that, was a study of this particular, concept. Then what we would do is we would have a rule that looks like this. And there's going to be exact parallel to what I did before a moment ago with binary sums. That's why I did it. Okay, so I will say, if you give me a number, I want to do something with that number. Okay? And you say to yourself, well, so to speak, what's the point of having a number? Okay, what good is it? You give me a number, 17, what good is it? Well, what it's good for is counting up to that. Okay? That's the idea. That's the whole point of having a number, is to count up to that thing. So what we're going to do is we're going to define, let's say, I am going to alter this, but we'll say we'll have a type C. Right? This is what you do in like Gödel's T. And you say, well, if you tell me, let me call it N0, which is of type C, which is what to do when the number is 0, so how to iterate 0 times. And as a function of the answer for our n times, I will tell you, I'll call it n sub s to be emphatic. I will tell you how to bump it up one more, which is the inductive step. Then I get a recursor, which works on m and n0, and I called it x.ns, okay, and it would have type C. So, for example, going back to a couple of lectures ago, I can now really define plus in the following way, right? I can define plus as lambda x in n, lambda y in n, rec, let's say we rec on y, and when y is 0, the answer is x. And if I get z, then I will do something like, I never know what to do here. What do you do? Successor of z, maybe. Okay, or something like that. Whatever it is. Yeah, I think that's the right thing. Okay, because this is the recursive call of the sum of x and y, and this will be the sum of x and successor of y. Yeah, I think I did it right, actually. Okay, but if I didn't, you should fix it. All right. Okay, so that finally, at long last, is the actual definition of plus. And then all the things I said about definitional equality for an ad hocly defined notion of plus will fall out here because the recursor is defined so that on 0 with n0 and x.ns will be definitionally equal to n0. If you want to iterate something 0 times, then that's what you do. And if you want to iterate it one more than m times, then what do? You plug in the iteration, the inductive The inductive hypothesis is run it m times, plug that in for x in ns. Okay? So those are the definitional equivalences that we will need. Okay, so that finally discharges my obligation that I've had hanging for a while about how you define plus, because if you take that definition and you crank it out with all the rules of definitional equivalence, you will see that either I made a mistake or modulo a mistake, the definitional equivalences I stated, the recursion equations I stated will be true. Okay, yes? I really...
Is the iteration principle rather than the recursion principle?
Well, yes.
Because without products, this thing is strictly
that's a
recursion.
terminological thing. This is perfectly fine. As long as I have Cartesian products around, I can do anything I want. So an exercise, define the predecessor. All right, and we'll define the predecessor to have type n arrow 1 plus n. How about? So if n is 0, the answer is, error. And if n is, a successor, you want it to be the predecessor. Define that using the recursor. It's using this recursion scheme. And it's a little bit trickier than you think. And my hint is use a shift register. Okay, this is what's beautiful. Oh, I love this kind of thing. It's a shift register. It's exactly like, have you ever done any hardware? What you're going to do is shift register. That's your hint, okay? No more hints behind that. So a hint, and we'll talk about it this afternoon in the problem session. Think of a shift register. That may or may not be helpful to you. So that might be like a distraction, but it's really true what you do. Okay, so all right, so we'll come back to that later. Okay, so this is what I want to do. All right, so that's what I would have done in the computational setting. But if I want to capture the principle of proof by induction, okay, so 2 would be, I really want to capture the principle of proof by induction. So I want to be in the dependent setting because I want to be talking about predicates. Okay, then what I need to do is generalize in exactly the same way. All right, I have to say, what you have is not just a type, but a family of types indexed by natural numbers. Okay? And then the idea is, what n0 is a proof that C is true, if you like to think of it that way. C is true for 0. This is exactly the usual thing. This becomes a little more complicated. I have to do something a little trickier here. Okay, what I have to do is I have to put in a number, so it's going to change a little bit. All right, I have to put in a number, and I have to put in the inductive hypothesis that, well, if I choose x appropriately, it happens to be the same x, then this holds for C, and then I show that ns holds for x plus 1. Okay, so this is the form, show C of 0, assuming it holds for x, show it holds for x plus 1, and then we have to modify this a little bit, so it takes 2 arguments like that, and then it's C, holds for whatever your m is. Works like that. And there is the general, so this is the, now by editing at the board, this is the rule for the general, the dependent case. Okay, so it builds in, so it expresses the induction principle. Notice that I can choose C to depend vacuously on x, and then I recover everything I did before because the substitutions are then vacuous, and I get back the original computation rule. So it's just a strict generalization. So notice what's happening is, this is a for loop, right? If you look at it as a computer program, this is a for loop, right? And it's doing a kind of flow analysis, okay? Because what is happening is when you type check, when you look at the properties of a for loop, you get to know something about which iteration of the loop you're in, okay? That's a way of thinking about it. So all these things about, these dreary, horrible things about flow analysis and program analysis stuff can all be expressed in a very clean way, okay, in dependent type theory. Okay, this is what is going on, and the critical idea is you're flowing the information about which branch you're in and what number it is into the branches of the analysis. Okay, that's what's happening. So again, it's like GADTs are like this, other things are like this. Okay? So this is the reason I emphasize this is because if you understand dependent type theory, you understand everything. That's the point, okay? And so it's kind of the master theory of programming languages. Okay, so this is so that's it for the natural numbers. Okay, now I want to do something that is a very complicated generalization of this idea. Okay, so we should be comfortable. Well, we should now take a moment because if you're not comfortable with anything I've said here, this is a very good moment to say that because I'm going to lose you big time in a minute. Okay. Y colon C, yes.
So you said it's related to the induction hypothesis?
Yeah, you can think of it as the inductive hypothesis, right?
But you're never really using it.
What's that again?
You're not using it.
Oh, I might be. I might be using it in here. Okay, this guy might refer to Y in order to do the recursive call. Okay, so the idea is that, so if you look, I should give you the new equations. To form the recursor, let me give you the new equation. So on 0, let me do that. Let's watch what happens, and then I think it will be clearer. So this will be n0. That's just like before. And then here, if you do the successor of m, okay, then what you do with x, y, and s, what is that equal to? Well, what you do is you plug in the predecessor along with the result of the recursive call on the predecessor. So you call yourself recursively on the predecessor, and you pass those two bits of data in as x and y in ns. I forgot who was asking the question somewhere over here. Oh yeah, I can't see you. You're right behind this other person. Okay, so does that make sense? Okay, so the successor step, the inductive step, gets to know what the predecessor is, and it also gets to know what is the result of the recursive call. So this is the IH, because this is the inductive hypothesis, because that is the proof that C holds for the predecessor for x. See, I'm plugging in for x with m, and this is rec of m, so that's the proof that C holds, inductively, that's the proof that C holds for that particular choice of m, and then I must pump it up one more and show that C holds for one more. Okay? You see what's happening? It's very good for us to pause on here because, as I say, if there's anything unclear, I should explain it because otherwise we will be absolutely out to sea in a second. Yep. Yeah, you do, because I have to be able to, you know, I'm slightly cheating here. I could call, I'm relying on alpha conversion that it's the same x, right? This is an x. So I'm relying on the same x here. If you wanted, I could use a different variable and then plug it in to make it a little more emphatic. But yes, of course you need that because it's a predicate, right? When you think about how you do a proof by induction, you're doing some induction on, you know, x or whatever. In the inductive step, you say, well, assume the property holds for x. I want to show it holds for x plus 1. So assume it holds for x, and I want to show it holds for x plus 1. It might very well be, I mean, I don't know what individually what your experience is. It might very well be that nobody has written out for you in logical form what the actual structure of a proof by induction is. You kind of learn to do it by a social process, quite possibly. And it may be that the idea of even specifying it precisely is new to you. I don't know. If that's the case, then you should expect it to take a little while to sink in, okay, what is happening here. Because the next thing uses this heavily, these ideas heavily. Okay, are we okay enough to go on or no? It's really up to you. I mean, you know, yeah.
Have an overview again of what we're trying to do, what we did and what we will do.
What we're trying to do with?
What you already explained, why you explained it, and what you're about to explain. Like
Yeah.
just very.
Okay. Well, what I'm going to do next is talk about identity types. And this uses the same ideas in a very more sophisticated way, I would have to say. Okay, so that's why so what I'm building up here, what I'm trying to accomplish is to get you to understand how principles of proof by induction are represented in dependent type theory. And the critical point is that you work with families of types indexed by the thing you're inducting over, and that you flow information into the branches that tells you which particular case you're in. That information about the inductive step flows into the branch so that you can say something in general about any M of an inductively defined type in terms of, well, its composition. So here it's an in left or an in right, or when we edited it with a Boolean, it was a true or false. And here it's a little more fancy. The possibilities for a number are 0 or the successor of another number. So when I do a proof by induction on that, I get an inductive hypothesis suddenly corresponding to the fact that this is a recursive process of building one number out of another. So I get to assume it for the predecessor and show it for the successor. That way I know, regardless of what M is, it must either be 0 or it must be the successor of something. And if it's 0, I am indeed giving you outright, by this definitional equivalence, a proof for 0. And by this premise, with this definitional equivalence, I'm giving you a proof for n plus 1, successor of M, okay, in terms of a proof for M. And that's what this is expressing. Okay? Yes?
Like reduction rules for Boolean and for natural numbers.
Yeah.
And we don't like proof terms that correspond to the.
Exactly, yes. So this is the induction principle, and those are the proof terms, yes. Okay, is that good? Is that the correct answer? That's the answer you wanted? Yeah. Okay, yes.
But I don't understand how they fall out of the definition.
How they fall out of what definition?
Of the recursive. So you have this rule for defining rank of n, etc. How do those definitions come out of that?
Well, by definition. I mean, the idea is I'm thinking of these two rules as an inductor definition of the elements of the type, by which I mean it's the least type closed under these rules. Okay? So the only thing that is in the type of natural numbers is either 0, because it's that rule, or the successor of one that's already been constructed, and nothing else. That's the so-called extremal clause. So this is an inductive, this constitutes an inductive definition of the type n. If you have any inductively defined type, and over here, these two rules constitute an inductive definition of the sum, of binary sum of two types, okay? Because there's only two possibilities. It's an in left or an in right. I'm enumerating them. Or if I, if I specialize that to Booleans, then this would be true and false. Those are the two cases. So, so-called enumeration types are just a form of inductive type. So in CIC, there's a whole general apparatus of inductive types, of which everything I'm doing is just a special case. However, to throw the whole general case at you becomes really opaque, okay? So I'm trying to do the special cases. Okay, so if you think of this as an inductive definition, then what I'm doing here is I'm reasoning from, so here's another way to write this rule. You could do it this way. It's exactly the same thing, but I could change the rule to look like this. I could write it, and we'll make this, I don't know, U. I need a letter. Okay, so I'm defining a map, and then this would be U over here. It's the same thing, but perhaps it would be helpful to do it this way. So I'm defining a mapping. So forget the gamma. I'm saying a mapping from n into, well, from u and n to u for xc, okay? That is, I'm giving a proof of u for xc uniformly in u. A proof by induction is always defining a mapping, okay? That's what you're doing. And this is the proof object corresponding to a proof by induction. So if you just look at these as like putting in truths, this says that's true, and assuming this is true, then forget that part, this is true, and therefore uniformly in n with u, that C is true. And that's what the thing is saying. And then the way you get this from that is the inversion principle. If this is the elimination rule, the definitional, the symbolic execution rules are always that the elimination is post-inverse to the introduction. So I have two cases to consider. Elimination applied to introduction 0, elimination applied to introduction 1. Okay? And then I give the equations that makes that work. Okay? So that's how that works. It's all, excuse me, it's all the same pattern. Still not happy.
It's okay. I'm just trying to understand on a higher level. Hold on. So you're thinking of so this P is what is usually a P. So it's like
There's a predicate you can think of.
it has yeah, okay. What's the difference between one and two that is non-dependent and one is
Oh yeah, it was just dependent or non-dependent. I thought by starting out with a non-dependent case might be helpful.
so dependent?
Yeah.
Dependent?
Oh, it means that I'm dealing with a family of types. That the elimination works is an induction principle as opposed to merely a recursion principle. Okay, so the first form, I don't no longer have it as a board, was strictly to do with computing. If you want to compute with a number, how do you write down a for loop? That was recursion. But if I wanted to express the stronger property of proof by induction, then I have to fill in, I have to have a more sophisticated understanding of the rule, which allows me to flow the information about which branch I'm in into the predicate. Now it's dependent, yeah. I edited it as a word, yes. Okay. Yeah, there was a temporal dependency there. I didn't leave them both up there. Okay? Are we all right? Another question?
Why do you write x comma y dot ns?
Why do I write?
What is that x comma y dot ns?
Oh, it just means this is my notation for I have a multi-argument operator, rec, and these two variables are bounded in here. I don't know what notation Frank used, but it must have been something that looked like that. Okay, so it's a generalization. You know, when you write, you can think of, when you write lambda x dot m, you can think of that as the operator lambda with one argument x in m. When you have case analysis, you have case and it has 3 arguments, and it binds a variable x in one argument and a different variable in principle y in another argument. So it can be written like that. It's a completely systematic way of dealing with binding and scope. Amongst many other places, you could look at my Practical Foundations book, explains all of this. Okay, it's not, conceptually it's what everyone does. In exact notation, it's probably not exactly what everybody else does, but it's conceptually the same. Okay, good enough? Yes, one more.
Can the C the type, dependent type, right? Depending on that.
Yes.
Can X be also a dependent type?
It can also be.
Can X like?
I didn't quite catch that.
Okay, so do we have like recursive dependent types? So can X also be a dependent type?
Something can also be a dependent type. I didn't quite hear.
X. So X, can X also be a dependent type?
What does it mean X? Do we mean X as a variable here, so I don't quite know what you're getting at?
Or like this, maybe like natural numbers, like.
Oh, and I see.
And also, I mean.
Well, yes. Let's not go there right now. Okay. Let's walk before we run. Okay. But yes. Okay. Yes. I mean the real of its generality works for everything, but as I say, if you go look up somewhere what the general formulation of inductively defined types is, it's kind of scary if you're not really, if you haven't developed the stomach for that sort of thing. So you have to, it gets complicated. It all makes perfect sense, but you have to build yourself up to it. Okay. Okay? All right. So we'll give you some practice with this. Maybe as a homework assignment, what I can ask you to do is take this, a similar thing. Let me jot down an inductive definition, and I want you to generate the rest of the story. Okay, so the inductive definition will be, I'll do something like binary trees. So what I will do is I will say the empty tree is a tree. And this is the simplest thing I can think of off the top of my head. And if I have 2 trees, then I can form a node which combines them into another tree. So this will be called tree introduction and tree elimination. Okay, and what I want to do is your exercise is a tree introduction. This is leaf for E, empty, and this is node, and then our exercise is define an appropriate tree elimination. Yeah, and its definitional equivalences. Okay, so we'll leave that as an exercise for you. Okay, so now what I would like to do is start revisiting this issue of equality, and this is where things will start getting difficult. Okay, so I spent a lot of time last night working out my story. So let's see how far we're going to get with this, how much trouble I get into, and how quickly. Okay, so well, to recap, what I've done so far is I've developed the basic framing, and I've outlined for you the basic framework of dependent type theory. And I've left sort of a gaping hole, you could say. So what I did is I introduced, structure like maybe we had all the propositional types, just to remind you. So maybe we have 1, 0, and we have A plus B, and we have A cross B, and we have A arrow B, and then I generalize these things, and I have pi x in A, B, and I have sigma x in A, B, and I put in nat for discussion, okay? So we put in at least that much stuff so far, all right? So this is the apparatus we have. And the glaring omission that I have from this, in order for pedagogical purposes, I also chucked in special case things like sequences of numbers up to length x, et cetera. And I put in a few other things there. But if you want to look at this as from the point of view of logic, and if you want to think of this as like universal quantification and existential quantification and implication and so forth and so on, then the thing I'm missing is the idea of equality. Okay? I don't have the idea of being able to express when two things are equal. So what I want to do is I want to introduce what is called the identity type, which in some sense is the most primitive, in a certain sense, the most primitive relation, which is to say binary family of types that you could possibly hope for. So here is the idea. I want to introduce this type, and it's written like this. So equality at A of M and N is going to be a type. Under what conditions? Pardon me, my allergies are bugging me. Okay, so we have this. Okay, so this is supposed to be the type of proofs that M and N are equal, and now we're going to put a question mark there because this is going to be a very interesting passage in my lectures here, are equal in some sense that we need to elucidate, okay, elements of type A. And what I'm going to do is I'm going to develop the principles of this as they're classically done, and then I will point out to you that we're in trouble, okay? That the thing is not really working the way you might expect. So that's where I'm going. So sometimes you could use other notation for this, like sometimes it's convenient to write M equals A, N. But the problem with that sort of notation, you can do that, and sometimes people will use squigglies or something. They use various notations. It's not standard. But the point is it's supposed to be a type. And there's also a judgment of equality, and it gets confusing. And so I'm going to reserve the equal sign for the judgment, and I'll always write identity for the type, so that I hope that will help avoid any any confusion. So this is a doubly indexed family of types, right? It's a family of types. So for each A, I have a family of types indexed by two elements of type A, M and N. Okay, that's what's going on here. All right, so that's the first point. So that's what a binary relation is. It's a propositional function. Thinking of propositions as types or types as propositions, it's a propositional function. Given m and n of type A, it yields a proposition, the proposition that expresses that m and n are equal as elements of type A. You see, the idea of type theory is that propositions have interesting structure, as opposed to the classical logic point of view, which is that there are only two propositions in the world, true and false. Okay, and then you just completely degenerate all of the structure. So what we're going to do is we're going to say, no, Booleans are data, propositions are something else entirely. Okay, and that's a very pernicious confusion that is long-standing confusion in the literature, and so I would want to draw that out here. So you must think of this, it's a proposition in the sense that it's the type of its proofs. Okay, all right, so that's the idea. So what sort of proofs are there of equality? Well, what we're going to do is we're going to axiomatize this. The first thing I'm going to do is I'm going to axiomatize equality. I would like to think of the identity type as an inductively defined type according to the following idea. It's the least reflexive relation. Okay? That's an inductive definition. In the same way that when I find the natural numbers, I say it's the least type containing zero enclosed under successor. I'm going to say it's the least type containing reflexivity. Or another way of saying it, it's the least reflexive relation, the smallest reflexive relation. It's the diagonal, right? If you admit only the diagonal and nothing else, then you've got the identity, right? That's the usual way to think about the identity relation, right? So, and in classical accounts of logic, the identity relation is utterly boring. It's merely the diagonal. That's because they've suppressed all of the information about what the evidence is for equality. All of the action from here on in will depend on undoing that mistake. Okay, so I'm going to axiomatize it as the least reflexive relation. So this would be called the identity formation. This is how we form that type. So what is the introduction rule then? What is the identity introduction rule? Well, it simply says that the relation is reflexive. And if I want to be careful, I'll put a sub A there, and I'll do this. So it says, if you give me m in A, then I will give you a proof that m is equal to m. And that proof is reflexivity. So you have to get used to this idea of proof objects. If you just read this as true, what this says is forget the m part, or you need to know the m part, but you forget this part, and it's just saying that it's true that m is equal to m. It's reflexive, okay? And it's the least reflexive relation in the sense that there are no other introduction rules. That's the only rule there is, okay? Because as the pattern with inductive definitions is, whatever it is I do as the introduction, whatever introduction rules I have, in this case there's one, I consider it to be exhaustive, okay? And now what I do is I express the fact that that's an inductive definition using a kind of an induction principle that lets me reason about it. So now this is where the exact same ideas I've been developing appear again, but in a somewhat more dramatic form. Okay, so let's look what we do here. Now, I know this is going to be tricky, okay? I'm sorry, I can't help it. Okay. I'm doing my best. All right. So let's try to figure out what we're going to do here. So what would what is the principle of proof by induction over the proofs of inequality? You see, I want to talk about reasoning inductively over the elements of this type. In fact, it might even help you at the moment to ignore the fact that I'm expressing equality. Just like suppress that. I've got some J random type, which I just threw up here, that is characterized with this one and only introduction rule, and to hell with what it's supposed to mean temporarily. Okay? Let's just do it. I think this may be the most helpful way to approach it. Okay? It's just an inductive definition. Okay? So, what am I going to do? What I'm going to do is I'm going to provide some kind of an induction principle. What did I call it? Oh, yeah, it's always called J. Okay. It's always called that. So we're going to call it that, okay? It doesn't mean a damn thing, okay? But it's called J. So what we're going to do is we're going to have J of something, okay? There's going to be some stuff filled in here. And it's going to be a proof of M for X. Well, it's going to be a little more complicated than that. All right. That's partly where this thing gets complicated. But we're going to use it to prove something. So the idea is that we're going to say, let me get my letters right, because if I screw up my letters, then I'll be endlessly flailing away here. So, okay, so let's try to get my letters right. So the general pattern of a proof by induction is I've got an unknown, unspecified object of the inductively defined type. So I've got an element P of the inductively defined type that's inductively defined by this rule. And I want to reason from that fact. Okay? So what I want to do is I'm going to leave a little space, but what I'm going to do is I'm going to compute on P in some manner, and I'm going to wind up with something that goes here. And there's going to be a question as what would go there. Okay, if I were not worried about dependencies and predicates, then what would go here would be some C, where C would be an arbitrary type. That would be the non-dependent form. The non-dependent form is next to useless, but I just want to help you get your bearings by comparing what I'm doing here with what I've done before. So this will have to get fancier, so don't take it too seriously at the moment. Okay, but this is the approximate idea. So what do I know about P? I mean, P is an arbitrary element of this type, this crazy type I came up with. So it must eventually boil down to an instance of reflexivity, because this is the only introduction principle there is. Okay, it's a complicated computation, but at the end of the day, when you run it, it's got to be reflexivity, in the same way with these other things. So that's the only eventuality I have to prepare for, right? I have to prepare for the eventuality that P is in fact reflexivity. So what that means is that there's some element X of type A, right, written like that, which is going to represent this term M. This is the argument to reflexivity, in the same way that we had an argument to in left or something over here. So this represents that argument, okay? And I'm going to compute on that basis. And if I were being dependent, if I were being non-dependent, which is not very useful, but if I were being non-dependent, then the J rule would look like this. And then the definitional equality would say, if you give me REFL of M with X dot Q, then that's definitionally equal to M Q. That would be the idea. This is not right yet. We have to make this a little fancier. But that would be like our first cut at it, right? From just a purely computational point of view, take an arbitrary P. It must eventually be a REFL. Be prepared to handle the reflexivity of some X. We don't know what X is. Okay, so Q is acting with reflexivity, and then I do that, and when it really is reflexivity, you just plug in that M for X, and we've got Q, and we're done. Okay, that would be good if that's all we had to do. But the truth is, I want to express a proof by induction, okay? And so the idea is I have to have some additional data over here. So now if we look at the sum, you'll notice, in the case of the sum, we had some idea of that C could depend upon the element of A plus B under consideration, because that's what gets plugged in. So we would want, by the same kind of reasoning, we would want, with Z being id A, and now I don't know what to write here, that's the issue, id A something or other, then I want C to be a type. And then at that point, we're going to want to plug in P for that Z inside of C. That's what we would want to do, okay? Because you see, C wants to be a predicate about the object in question of this inductive type. Okay, good. That's what we want to do. However, in order to behave generically, right, I need to say something about what goes in here and here. So the idea is it's an inductively defined family of types. You see, that's the trickiness here. Unlike the natural numbers, this is like someone asked this question earlier, and now this is where it comes up. So unlike the natural numbers, where you just have a fixed type that is inductively defined, it would be as if the m and the n were suppressed, like it's just id a. Okay, then we wouldn't have any problem because we would just write id a here, and z would be that, and we'd plug in p, and we'd be off to the races. We'd be good. Okay, but this is not a single inductively defined type. I am simultaneously inductively defining an infinite family of types indexed by pairs of elements of type A. That's where it gets complicated, and I think that was your question. Okay, so now I'm answering it. Okay, so what we have to do is that I did this wrong. It should be a comma. So what we have to do is we have to have an XA and a YA, and Z is an arbitrary proof of X, and C gets to depend on X, Y, and Z. So C has to be a family of types that's prepared to work for any two elements of A and any proof that they are equal, or any element of this weird inductively defined type. So that here, what do we plug in? So something goes in for X, Y, Z inside of C, and what should it be? Someone tell me? What is the inductive step? What is the generic case that I have to prove? You should be able to tell me now what things. So the three things get plugged in, one for X, one for Y, one for Z. What do I plug in? Someone have it a go. I can't tell who's talking. Yeah? It's hard for me to hear you.
The last one could be reflexive.
Reflexive of what?
Reflexive of A with
Yeah, with the what argument?
identity.
With what?
Okay, maybe with P.
No, with X. I think someone said, yes. So what you want here is this to be a raffle of X. True, because in the same way that over here you plug in left of X, right, into C. So I'm plugging in refl of X for Z, okay? But and this is the X in question. But what do I plug in for X and Y? Because you see, C is assuming you're giving me a proof of reflexivity of something. So reflexivity is a proof of, it's an element of identity of what? X and X. So this is X, X. Okay, that's what goes there. Okay, and then here, what I plug in is, I've forgotten. Oh yes, M, N. Let me write it out. M, N, and P for X, Y, Z in C. And then the computation rule remains the same. It doesn't change. It's just I have a more precise typing. And this is the idilim. Okay, so here's a way of saying it is. If I want to prove something about a proof of an identity, it's enough to prove something about the reflexive instance, because the identity is the least reflexive relation. So an induction principle always reduces an abstract situation to a concrete one. So with mathematical induction, you say, oh, I want to prove something about X of type natural number. It suffices to show that the thing I want to prove holds for 0, holds for 1, holds for 2, holds for 3, holds for 4, holds for 5, holds for all infinitely many concrete instances. You say, if I can do that, then it's sufficient to work for an abstract X. That's what a principle of induction is. Over here, when I do case analysis, I want to do a principle. I want to reason by induction over M, which is of type A plus B. Who knows what M is? It suffices to cover the two concrete instances, in left of blah. Well, it's not two, it's infinitely many, but two forms. In left of something and in right of something. And if I can prove it for each of those, then for all of those infinitely many cases, then I have proved it for the general case, the abstract case. So that's what's happening here. I have an unknown proof, all right, of the identity. It's enough to prove something on the basis of it being reflexivity, which, of course, relates X to X. Okay, that's the idea. All well and good, but now it's going to get really hard. Okay, so I'll show you some things next. Okay, are you with me so far? I fully admit this is a non-obvious thing. And by the way, a lot of times people will put like X, Y, Z dot C down here as a kind of parameter to J. That's why I left room there. And this type, I should have told you this before, in all of these inductive types, there's a nice terminology. This is described as the motive. Okay? And the same would be true over here. This third-party type that is participating in the induction is called the motive. So a lot of times it's just nice to have a word for that, and that's a nice word for it. Okay, so we can call that the motive. So often the motive is written as a kind of subscript on J. That's a technical detail about the syntax that I'm being rather cavalier about in my lectures because it becomes too, you can't deal at such a level of detail all the time. Okay, so I'm being a little cavalier about it, but often people will put the motive on J. Okay, so that's called the J, or identity elim. Okay, in the Nordstrom book, J is called ID peel, which is not my favorite term, and nobody else has ever used that term as far as I know, so that doesn't come up. Okay, and in a very general framework of inductive definitions like you have in CIC, this whole thing is just a special case of an inductive type, and everything is like, emerges from the general case. Yeah.
Whenever we define a new logical connective, we define like the coherence properties, like the reduction and the expansion, to make sure that the intro and lim rules actually make sense.
Yeah.
Is there something we could prove for this, to make sure this really complicated thing that we've just written down?
No, you see, that methodology is a bit problematic.
Okay. Is there a less
The best way to explain that is through category theory, and that's what Steve will be talking about eventually. And in the category theory, there's basically what is called a universal characterization of the connectives, and and it's their universal character that corresponds to that principle of local soundness and completeness, and I'm going to leave it at that. Okay, so a full discussion of that is best carried out in the language of category theory. So that's my dodge.
If I can interject, though, the equality that you have there, isn't that a local reduction? Isn't that the reduction that shows that the elimination matches the introduction?
That shows that what?
That the elimination matches the introduction, the fact that your reduction...
Yeah, so this is the lim of intro, yes.
Yeah, so that we have.
That we have, yeah. But the universal part of it, Steve will get to this. Okay, I'm going to dodge this, okay? There's a universal condition, and if you don't know what a universal construction is, that's something you need to learn in category theory, right? One of the most important ideas in category theory is this idea of universal construction. And he will explain things in terms of universality. So it will emerge out of the fact that N will be something called an initial algebra for a functor. And the initiality expresses a kind of universal condition that corresponds to the thing you're alluding to. Anymore. Otherwise, I'm going to now start lecturing in category theory. So, okay, so I'm going to dodge that question. Okay. All right, are you with me so far? Okay, so now we'll have some little puzzles for you, and some some very interesting things happen. Okay. So what I would like to say, this is where the fun begins. So what I would like to say is, what we have done with the identity type, the terminology is to say that we have, in a certain sense, I'll just scribble it here for lack of a better place. What we've done is we've internalized equality. So equality is something we were talking about from my first lecture, the idea of equality of proofs. And what I've done is I've internalized the concept of equality as a type. Okay? I have a type of proofs, of evidence, that things are equal. So I've internalized it into the theory. Okay? So as it will come out in the category theory, what I've done is a kind of internal HOM, it's called. Okay? And you will see how that comes out later on. Okay? So I've done an internalization. The identity type, by the way, for those of you who are au fait with such things, should be thought of as a HOM. But we will we'll get to that shortly. Okay? That has to do with something called the groupoid structure of the identity type, and I will get to that in a minute. Okay, in order to get my way to the groupoid structure of the identity type, what I would like to do is, first of all, do some very trivial things. So, first of all, I would like to prove that equality is symmetric. Now, this is a very simple one. And I'm going to give you, as a homework exercise, the proof that equality is transitive. And I'll give you a hint in a minute. This will be homework. It's substantially harder, but I'll show you how we deal with equality of symmetry. So what do I mean by that? What I want to say is that, let me check my letters to make sure I say everything in the right sort of way. So here's one way to do it, okay? So for any m and n, I will say, if you give me a proof that m is equal to n, I can turn that into a proof. I'll call it sim of x. I'm going to define what that is, which is a proof that id a and m. And in fact, the other notation, sim of x, can also be written as x inverse. We'll see why in a minute, okay? The reason is that what I'm heading toward is the idea of what is called, what I mentioned a moment ago, called a groupoid. A groupoid is best thought of as, you could say, a constructive equivalence relation. It's an equivalence relation that's equipped with evidence. So we'll come back to that in a minute because there's something really beautiful there. Okay, but first let's see. So we're going to define. So we're going to define sim such that. Okay, excuse me. Define sim such that this is the case. So for any proof of m equal to n, it turns it around and gives you a proof that n is equal to m. And how we're going to do this, and as a matter of honesty, you know, I spent a good 10 minutes or so last night while watching TV trying to figure out the damn proof. It took me several times. I have it crossed out here in my notes. You can see. So I didn't get it right the first time either, so let's do it. Okay, so the trick on these proofs is to find the right motive. Okay? So what I want to do is I want to find the right motive. Okay, that's the hint. And the same here is going to be, the hint is find the motive. Once you know what the motive is, you've got everything. Okay? So we've got to do this. So let's watch what we're going to do here. So I'm going to just do this one. I'm going to, you know, we're getting nearer to lunchtime. So I'm just going to pull this right out of my, out of the air and tell you that the motive in question is this. Oops. It'll seem like magic. Okay, this kind of proof is sort of a magic thing because I will show you that it works, but it's just like the worst form of blackboard math. You know, you just say, ha ha ha, here's the proof, and you cover your tracks. You don't say anything about how you found it. Okay, so the W plays no role here. I could play some underscore. Okay, so this is my motive. That's my C. Okay. This is going to be the motive in this particular case. That's my C. Okay, my C. So what I want to do is I'm going to define sim, okay, to be a J with that motive, so I won't write it down here again. That will be my motive for J. And I will do induction on X. Okay? And it helps me if I use the, the right notation. Yeah. So we'll do y here. It'll be y dot something. Okay. I'm going to define it to be this. And the point will be, right, that this at the end will have type id, well, it's going to be, let's do it out. It will be plug in m and n for u and v, and plug in x for nothing because it's not used. So its type will be plug in m and n, oops, for u and v in id a vu. So that, of course, is id a and m. That's how I got it. Okay? the way I found the motive was, I know that whatever I'm going to do here has to be, okay, the result of the J will be plug in Mn and, well, X, but it doesn't matter, okay, for U and V inside of something. So I swapped them in order to get id A and M, which is what I wanted, okay? What I'm doing up here. So what goes in here? Well, the thing that goes in here has to be, what is the type of the thing that goes in here? So this will be, call that Q. And Q has to have type what? Well, I have to need a notation. Given X in A, Q has to have type the motive instantiated with X in X. So it's id A, plug in X and X, right? Because that's right up here. X gets plugged in. So I do that. Okay, so what should Q be? Well, just make it, oh, I called it Y, so let's call this Y. What should Q be? Well, let's say refl A of Y. That's of type, oh, that would be Y again, then sorry for the change of variable. Okay, so it would be refl Y. So this guy is refl. And we're done. So what I've done here is I've argued, it's from a certain point of view it's trivial, but I'm leading you somewhere, okay? So from what I've argued is the least reflexive relation is symmetric. Of course, if you picture it as the diagonal, that's obviously symmetric matrix if you want to think of it like a matrix, a 2 by 2, or excuse me, a two-dimensional thing. Obviously it's symmetric, okay? So that's what I've done, okay? That's what I'm doing here. All right, so what we're going to do with equality is transitive. What you're going to do is you're going to find trans of xy such that given a proof of m and n, and given a proof of n and p, I'm going to say trans xy is going to be a proof of id a m and p. Okay, that's the exercise. In this notation, this is often better written as y after x or y times x, if you want to do it like that. But let's use composition. It's going to be composition. It is composition. Okay, why is it composition? Why is that the right way to think about this? Well, let's see. Let's see what's going on. You know the notion of a Hasse diagram, right? The idea where you draw arrows around points to indicate when things are less than each other, right? So what I do is I say, well, every element, if this is a point in A, then we can say says that it's less, that point is less than itself. And we can label that with information. That's refl. Let's say it's x. If this point is called x, then refl of x is evidence for the fact that x is equal to itself. Then we have a rule that says if you have points x and y, call them points x and y, and you have some proof p, okay, that that tells us that, oh, I see, that tells us that x is less than or equal to y. That's the intuition. Then what I do is I say, oh, and moreover, there is an associated map, P inverse, or sim of P, which tells us y is less than x. So let's just write it like that. I don't need the dots, really. Okay, I can write it like that. And then transitivity says, if I can go from x to y by P, and if I can go from y to z by Q, then I can go from x to z by doing Q after P. That's what is being said here. And this was this is transitivity. So the idea is if you think of this, the arrow is representing, so this represents the idea that x is, so to say, less than or equal to x. But it's going to turn out to be a symmetric and transitive relation. So I could use for my preorder a notation like triple bar or something. Oh, I better not do that. I need some, let's twiddle, I don't know. Okay? So x is related to x. And this tells us that if x is related to y, then y is related to x. And this tells us that if x is related to y and y is related to z, then x is related to z. Oops, X is related to Z. That's what is being said here. But, what I'm doing is I'm equipping things with evidence because I'm a good constructivist. There are no just bald facts in the world. You have proofs of them. Okay? So these are the proof objects. Okay? The proof objects. Okay? So there are proof objects that witness the symmetry and transitivity of the internalized equality. That's what I'm writing down. So now what you start to see is I have some structure. And the structure I'm beginning to have is, if you look here and here, I have the structure of a category. And if I look here, I have a structure of a category in which every map is invertible. Okay? That is called, begins to be, it's heading towards, I'll write towards because there's something else needed, it's heading towards what is called a groupoid. So we might call this a pre-groupoid. Okay? So we'll call that a pre-groupoid. Why do I call it a pre-groupoid? Well, because we need some additional conditions. So I'll make some words for ourselves. Okay? And the additional conditions we're going to need are the axioms of a groupoid, which tell us that in some sense, P inverse after P must in some sense be equal to, whatever I mean by that, and that we're going to come back to, the identity or reflexivity. So this reflexivity could also be written identity. Okay? So this is reflexivity or identity. Okay? And it should be that P after P inverse in some sense of equality should be the identity. Plus we should have associativity, don't make me write it out. Okay? And unit elements. So we should say if we have the identity composed with P should be in some sense the same as P, and P composed with the identity should be in some sense the same as P. Okay? Plus associativity, and if I didn't miss out anything, then we have the structure of a groupoid. You can look at it as a generalization of the notion of a group, because we have identities, we have inverses, and we have multiplication. Okay? So unit element, inverses, and multiplication. So there's some structure there that looks like a group. It's called a groupoid. Okay? So what I'm doing here is I'm trying to elucidate, I'm trying to bring out the groupoid structure of the identity type by doing these two examples just to find. I haven't considered these yet. These are big question mark. I'll come up with this later. So another way to think about this, because we're getting to lunchtime, so let me close off. So another way to think about this is that we can think of these proofs of identity as paths in a space. So the idea, this says there's always a path from X to itself. Now, that path is a little hard to draw because the identity path is really the one that doesn't go anywhere at all. Okay, because if I think of this as sitting inside some space, A, this kind of looks like it goes somewhere and like crosses through other points. That is not what I mean. It's very difficult to depict, okay? I really want the path that doesn't go anywhere, okay? So, but we often draw it like that, and by labeling it the identity, I'm reminding you that it's the path that doesn't go anywhere. And so this says, if you're in a space like A, let me go back here. If you're in a space like A, and if you have a path, we'll draw it as a kind of wiggly arrow from sort of X to Y, then you can turn that path around and you can go back the way you came. So that's its inverse. And then the other is that if you have a path from X to Y and a path from Y to Z, then I can compose those and get a path from X to Z. And of course, therefore, back. All these things go back, or I could notate this another way, which is to just put a bidirectional arrow, because we think of paths as being reversible. Okay? And we get diagrams like that. Okay? And this concept of a path is a central notion in the idea of what is called homotopy theory. Okay? Is the idea of paths in a space. Okay? So you can think of it as ways in which what it can be thought of is that it's okay to move from X to Y because I can walk along that path. I can squish X and Y together because there's a path between them. I can walk X along Y and contract that path. Okay? The space is contractible in a certain way. All right? That is the idea. And then what you do is you look at the contractibility properties of paths in order to say something about the overall structure of the space. And the particular example that people usually do is if I put a little box here to indicate a hole in the space, so A consists of everything but that, then I cannot contract this path to this path because you can't get past the hole. Okay? And so those issues of contractibility are what tell you something about the overall structure of the space. Okay? That is the idea. Okay? So here's something that is like extremely kind of geometric and topological in flavor, but in fact, it is given beautiful and direct expression in constructive type theory. Once you start seeing this, I'll develop these ideas further, then you can understand why I am such a fervent believer in type theory, okay? Because there are no accidents in the world. This is not like some random coincidence, okay? This is telling us that computation, the essence of what type theory is all about, is at the bottom of even things that seem so far-fetched and abstruse and far afield as, you know, deformations of spaces and of topological spaces, is actually an issue of computation. And it turns out a lot of things that are done in algebraic topology to understand the structure of spaces amount to functional programs. You'll be amazed at what they're doing when you finally realize that they're really talking about functional programming with dependent types. It's astonishing, extremely beautiful. In fact, there's a whole year of program being devoted to this in Princeton next year. Starting this year, people are talking about these ideas. So this is the beginnings. So the reason I say it is by way of getting you motivated, okay? So see if you can figure out how to define transitivity. It's not easy, okay? But the hint is find the motive, okay? If you can find the right motive, then you'll be off to the races. Okay, so I'm going to talk a lot more about these issues of equality in my next lecture, and we'll come back to some of this. Okay, so I hope that whets your appetite and